Good afternoon, everyone. It gives me great pleasure to introduce today's distinguished lecturer, Shelley Glashow. I've known Shelley for many, many years and am proud to have called him colleague as we were both faculty members at BU. Shelley got his PhD in, I believe, 1959 under the direction of Julian Schwinger, one of the great physicists of the 20th century. He then moved to the Niels Bohr Institute, where he wrote one of his most famous papers and followed that up as a postdoc at Caltech, and subsequently had faculty positions in an ever-improving list of institutions: Stanford, Berkeley, Harvard, and then Boston University. He is currently the Metcalf Professor of Science and Mathematics at Boston University, where he has been for, I think, almost 17 years now. Shelley is one of the great physicists of our time. He is well known to most of you as one of the founders of the so-called Standard Model of Physics. Our understanding of the fundamental interactions of nature is in many ways due to Shelley's work from the early 1960s, and it has a tremendous and profound impact on all of us who do physics. Shelley is also an interesting thinker about how science works and how it proceeds. And over the course of my many years affiliation with him, I've learned a great deal about how to think about science, how it operates, and its role in human society. Today, he's going to tell us some of his thoughts about how science proceeds, whether it's by blind chance or by intelligent design. I should notice a couple of items on this slide. So first of all, I guess I'm welcoming you all to Chengdu. So I guess sometimes Shelley is not quite sure where he is. Also, the talk advertised on the poster includes an extra word in the title, one of my favorite words in the English language, serendipity. So Shelley, I know, has a fondness for language. He's very good at using it. And we've had many fun conversations about the origin of words. And so I wanted to tell him something that he probably doesn't know, which is that in a recent poll of Britons, serendipity tied with two other words for favorite word in the English language. And I challenge you to come up with a title that incorporates the other two words as well, which are nincompoop and discombobulate. Okay, and on that note, Shelley, it's a pleasure to welcome you here.
I did give this talk before, and that was at a conference on serendipity given in Chengdu over a year ago. And I liked the talk, so I decided I would give it again. Let me see if this thing works. Yes. So, introduction. There are some scientific advances like X-rays and penicillin that are not planned. They are unexpected and stumbled upon by accident. Others, like the drug streptomycin, like nuclear reactors, like so much else, result from careful planning and specifically targeted research. The history of science shows that both methods are essential, a fact that must be borne in mind by aspiring scientists and especially by governments, academia, industrial agencies, others who are seeking to foster scientific and technological progress. Thus, the answer to the title questions, to both questions, is yes. Some scientists focus on well-defined goals. First, they lay careful plans, then they look. Others have much more fun. First, they look, and sometimes they find something very interesting. The two quotations I will give two quotations that illustrate the dichotomy. Near the end of the 1700s, the philosopher Immanuel Kant who's the favorite philosopher of the ex-president of our university. Anyway, Immanuel Kant said, accidental observations, this is the Kantian road to discovery, the method of careful planning. Accidental observations made in obedience to no previously thought out plan can never yield a scientific law, said Kant, which reason alone is able to discover. Reason must not approach nature as a pupil who listens to everything the teacher has to say, but as a judge who compels nature, the witness, to answer questions that he himself has formulated. And that is the basis to what we teach our students in school in America as the scientific method. Kant did not experience the cascade of discoveries that were about to be made, many of them accidental. To Kant, science was a purely cerebral and methodological pursuit. His words recall what I was taught as the scientific method: frame a plausible hypothesis about nature, then test it by experiment or observation. Scientists sometimes do that, but sometimes they simply listen to Mother Nature. Serendipity, one of our favorite words. I'm not so much enamored of the other words on your list. Coined by Horace Walpole, a writer, borrowing it from the title of the fairy tale, The Three Princes of Serendip, whose heroes were always making discoveries by accidents and sagacity of things they were not in quest for. And I shouldn't say it, but serendipity is like looking for a needle in a haystack, but finding the farmer's daughter instead. Should scientists follow Kant and ignore accidental observations, or Pasteur's advice that chance favors the prepared mind, or the Roman general Terence's order that you must by skill make good what has fallen by chance? Serendipity and rational planning are as intertwined as are particles and waves. Some explorers set out to circumnavigate the globe and do just that, whilst others set out for China and find America instead. Since I'm in China, who can resist? Searching for the elixir of immortality, Chinese alchemists in the Tang dynasty mixed saltpeter with charcoal and sulfur. The powder exploded. According to a contemporary text, smoke and flames resulted so that their hands and faces were burnt, and even the whole house where they were working burnt down. They had stumbled upon the discovery of gunpowder, allegedly a serendipitous discovery. A second, perhaps more mythological discovery: the wife of the Yellow Emperor, upon taking tea in the shade of a mulberry bush, had a cocoon fall into her cup. It readily unwound and came apart as a long and delicate filament. Twisting the fibers together, she made a thread with which she wove a robe for her husband, the emperor. He loved it, and together they started the successful Chinese silk industry. So it is said. Another serendipitous discovery. And surely the great Chinese discovery of the magnetic compass was serendipitous. It could hardly have been otherwise. Anyway, that's so much for China. Now, here are some other serendipitous moments. In 1781, William Herschel, who was a great astronomer, he was also a great bassoonist and has written some wonderful bassoon concertos. In any case, he had come to America and built large telescopes and accidentally spotted a new planet. Later on, he accidentally discovers infrared radiation, completely serendipitous discovery. In 1820, Hans Christian Ørsted sees magnetic effects of electricity. Previously, there had been no empirical connection. There were analogies between electricity and magnetism. Both are forces that act remotely, but there was no relationship directly between them. He saw, while teaching a physics course, quite by accident, when he was trying to demonstrate to his students that sending an electric current through a thin wire causes the thin wire to get hot. He was concentrating on the thin wire, and his students said, "Hey, teach, the compass needle started moving in funny ways when you turned on the electricity." And that's how he discovered the connection between electricity and magnetism. And Faraday, in 1831, sees electrical effects of magnetism. He went on to search for whether he could find a relation between gravitation and electromagnetism, but in that respect, he was unsuccessful. In 1895, the world's first X-ray photo shocks Mrs. Rankin because everybody saw the newspaper article with the bones in her hand and her marriage ring visible, and she and other women were very concerned that women were no longer secure in their dresses because they could be seen with X-rays. Radioactivity, in 1896, this was one of the most serendipitous discoveries ever, and I will come back and talk about Becquerel's discovery, because in my mind it is the most serendipitous of all discoveries. He was certainly not looking for what he found. In 1928, penicillin. In 1932, the positive electron electrifies Carl Anderson. He did not know anything about Dirac's prediction of the positron just a year or two before, but he found it, and it was also the year I was born. In 1943, Albert Hofmann trips on LSD and discovers the wonderful world of lysergic acid. 1974, my friends Ting and Richter simultaneously spot the J-psi particle on opposite sides of the American continent. That's, of course, the first particle containing charmed quarks. We'll back to that later. In 1984, buckyballs were first sighted. That was an accidental discovery. And in 2004, the first accidental synthesis of graphene using Scotch tape. Lots of serendipitous discoveries. The letter K means a discovery. Might as well use this pointer since I have it. Is a discovery that is Kantian, meaning according to the scientific method, according to rational planning, whereas S is for serendipity. We're talking about the electromagnetic spectrum, which it all began perhaps with Isaac Newton. Isaac Newton that's rather deliberately set out to study the nature of light. Nothing serendipitous about this discovery. That he was able to split sunlight into its component colors. What is interesting is that he chose to define precisely 7 colors. And if you go and look at Newton's optics, you can find a marvelous illustration in which the correspondence between the 7 colors and the 7 notes of the musical scale is given in detail, with even appropriate spacings indicating the illustration coincides with the tuning of a piano with half notes and full notes, and the colors were divided in accordance with precisely that scheme. There was no question that Newton had in mind the wave nature of light, but he sort of put it out of his mind in some mysterious fashion and continued to insist that light consists of particles. Then serendipitously, we come to Herschel, who discovers infrared radiation. He asked the question, he set out to do the following experiment. He would determine what color carries heat, because he knew that if you go to the beach, you feel the warmth of the sun. Was it the red light, the blue light, the green light, whatever? And so he had 7 different thermometers corresponding to each of the different colors. And then he had some leftover thermometers which were lying on the table, and he split sunlight into the 7 colors, which fell on the 7 things. They all got a little bit warmer, but the one that got warmest was the one that was accidentally lying beyond the red. And so completely by accident, he discovered infrared radiation. Interestingly, Johann Ritter, a contemporary of Herschel, he did a lot of interesting experiments. He showed how he could use electricity to give himself an orgasm. That's what he did. But anyway, he also, using the Kantian philosophy, argued that by Kantian rules of symmetry, if there was something funny going on at one end of the spectrum, there had to be something going on at the other end of the spectrum. And so he managed to discover ultraviolet radiation. You might think he would do that with a piece of photographic film, but of course photographic film had not yet been invented at that time. He used little crystals of a silver compound, which were known to turn black when exposed to light, and they would turn black when exposed to the invisible radiation. But that was a Kantian, very Kantian discovery, as was the discovery by Heinrich Hertz, one of the first experimental physicists to be also a theoretical physicist, because like Maxwell before him, he could do experiments and he could understand theory. Hertz, understanding Maxwell's theory of light, was able to produce radio waves and broadcast them across the laboratory. And it didn't take very long before these radio waves would be used for wireless telegraphy. 1894, serendipitously, Mr. Roentgen discovers X-rays, whereas here in 1964, serendipitously, Penzias and Wilson discover the cosmic radiation background. So much for the electromagnetic spectrum. We are, of course, all of us, in what we see, feel, hear, smell, taste, or do, electromagnetic creatures. Everything is electromagnetic. In fact, it was the famous physicist Casimir who gave a wonderful lecture at one point in my youth explaining the electromagnetic nature of everything in the terrestrial universe. For the theory of electromagnetism, we are indebted to surprising observations made by Galvani that led Volta to the electric battery, Ørsted's accidental discovery of the magnetic effects of neutral currents, and by Faraday's accidental discovery of the electrical effects of moving magnets. I say accidental because the effect he was looking for did not exist. He found something that he was not looking for. And of course, let us not forget Coulomb, Ampere, Ohm, Maxwell, Marconi, and all those other people whose activities were completely planned in detail, especially Marconi, who worked hard to develop wireless telegraphy successfully. The most of all serendipitous discoveries. Mr. Becquerel was of a family of physicists. Becquerel was an interesting character, by the way. His most famous student was, anybody guess? Marie Curie. And Henry Becquerel was a family of physicists who studied luminescence or cold light. Upon the accidental, and by the way, Becquerel's father and grandfather working together were the discoverers of the photoelectric effect, of the fact that light can make electrical currents, the whatever you want to call that. Becquerel, when X-rays were discovered, he conjectured that luminous bodies, luminescent bodies, bodies that when exposed to sunlight or in any kind of intense light, continue to shine for some hours afterwards. He was convinced that luminescent bodies also emit X-rays. That was his hypothesis for the scientific method, that luminescent bodies emit X-rays. So to test this brilliant idea, he exposed a luminescent chemical to sunlight and placed it atop a wrapped photographic plate with some metal object between. And when he developed the plate, it showed an image of the key. So clearly, that to him, that meant that luminescence produces X-rays as well as light. But when he tried to do the experiment again, unfortunately, he was in Paris, and it was Christmas time in Paris, and there was no further sunlight to be had for the next 2 weeks. So nothing happened. He was unable to do the experiment again. Of course, had the sun come out, he would have done the experiment again. He would have published the result. He would be infamous for making the false discovery that luminescent materials produce X-rays. So waiting for a clear day, he placed this material in a closed desk drawer, and after many sunless days, he developed the film and was amazed to find it was exposed. So clearly, the effect had nothing to do with sunlight and nothing to do with luminescence and nothing to do with X-rays. It had to do with uranium, which by accident, by complete accident, a uranium salt had been the particular luminescent material that he chose to work with. So this was an instance of triple serendipity. What if the luminescent chemical he had chosen had not contained uranium? Lord knows there are many luminous materials. What if the skies of Paris had cleared so that he could confirm his original result? And what if Becquerel, to the amazement of his son, his son was amazed that Becquerel bothered to develop this thing that was in the dark desk drawer. Yet he did it, and because he did it, he made his great discovery. It was quite an incredible triple accident. Passing on to chemistry for a moment, certain elements were discovered, not many of them, accidentally. Most of them not. Phosphorus, discovered and named by Hennig Brandt while trying to produce the elixir of immortality from human urine. Didn't do that, but he certainly found an interesting chemical, and which it's a white solid. He was able to extract white phosphorus from urine. He went to a church at midnight and wrote on a piece of parchment the name of God, which then caught fire all by itself. It was a very impressive discovery. You see the linkage that always exists between religion and science. Hydrogen was first described by Robert Boyle as a gas which was produced when iron was treated with acid, and it was a liberation which he, Boyle, called the inflammable solution of Mars, Mars being the planet that has to do with iron, a gas later dubbed hydrogen by Lavoisier. Iodine was discovered accidentally. A guy was trying to produce saltpeter from seaweed, but instead he discovered iodine. Argon was a long and interesting story, was discovered by Lord Rayleigh when he was trying to measure the atomic weight or the molecular weight of nitrogen. had something to do with the idea that atomic weights were sometimes thought to be integers, and he wanted to find out whether that of nitrogen was a precise integer multiple of that of hydrogen. Well, of course it wasn't, but he made two different, to be absolutely clear, he measured the molecular weight of nitrogen in two different ways and had two conflicting results. And the result, in one way, he extracted nitrogen from air. In the second method, he decomposed ammonia into nitrogen and hydrogen. And the nitrogen he got from the air was denser than the nitrogen he got from decomposing nitrogenous materials. Eventually, he realized that he had discovered that, to the amazement of chemists, this is 1894 when chemistry was a mature science. I mean, the German dye industry was making money hand over foot, but chemists had not yet discovered that 1% of air is an element they had never heard of. Neptunium was the most recent, the last element to have been accidentally discovered. Of course, well, that's a long story. I don't know if I'll talk about this. I don't know how long I'm supposed to speak. And am I speaking too slowly or too quickly? Any particular? Just right. Just right? Okay, then let's go on. Let's speak about Tyrian purple. Purple used to be the most precious of dyes. Purple was produced from fermented sea snails, making such a foul odor. Now, this is unbelievable, that Jewish wives, according to the Jewish church, the Jewish rabbis, that Jewish wives were permitted to divorce husbands who became dyers without any excuse. The secret to his manufacture was lost by the Crusader conquest of Byzantium in 1204 AD, and that led to a tremendous problem because purple was such an important color. In then we come to 1810. Atomic weights seem to be integers. I mentioned that before. William Prout claimed that all atoms were made of hydrogen atoms. Of course, he was, in a certain sense, correct. And then, interestingly to me, I found that Mr. Prout went on to attempt to discover a purple drug, a purple dye, and he extracted what is today called murexide from snake feces and tried to commercialize it with no success. Organic chemicals were believed to contain a vital force, of course, so they could not be made from inanimate chemicals, until in 1828, Frederick Wöhler surprised himself by synthesizing an organic chemist. And he wrote to a vitalist colleague, "I must tell you that I have prepared urea without requiring a kidney nor an animal. This discovery was the first to cross the organic-inorganic divide. The false notion of vitalism may live on, but only among the credulous," which might include TCM or might not, but I will not comment on that. Serendipity and the color of money. The dye industry. I'm going to talk about a number of dyes in 1704 using cheap, contaminated reagents. Paintmaker Diesenbach, someplace in Germany, accidentally produced the first synthetic coloring agent, iron ferrocyanide. Artists ever since have depended on Prussian blue. In 1846, now we come to the most striking serendipitous discovery in the dye industry. We had this 17 or 18-year-old English young man who wanted to be a chemist. He was told by a well-known German scientist passing through that he should try to synthesize quinine. And so he set out to synthesize quinine from the destructive distillation of wood or coal or something like that. And instead of the brilliant white crystals of quinine, this is 1846, quinine was not synthesized for almost another century until its synthesis was completed during the exigencies of the Pacific War, because America needed quinine for its soldiers. It was synthesized at Harvard in the 1940s. So there was no way he was going to make quinine, but he made a sticky, smelly mess with a tinge of color, from which this young man extracted the first aniline dye, which became known as mauve. It was worn by the Empress Eugénie of the Second Empire in France. Queen Victoria wore mauve dresses, gowns. It became a color sensation. Every woman wanted mauve, and Perkin, who maintained control over the drug, became a very wealthy man. A few years later, his mentor, the German chemist who had visited England and told him to synthesize quinine, chanced on, again, another accidental discovery, the second aniline dye. Stupidly, he failed to patent it. He called it magenta. Now, historically, that's a very interesting name, because magenta was the name of a battle where Italy defeated Austria. Why would a German physicist name his drug where the German-speaking army was defeated by the Italians? I'll leave that question open. In any case, he discovered magenta and went on to discover other drugs and to create the vast German chemical industry. But we're not over yet. In 1863, another chemist searching for a new dye came upon a brilliant yellow chemical that had an extremely, for 26 years he tried to market it as a yellow dye, but it wasn't a very good yellow dye, but it turned out to be explosive. He had discovered TNT. Now, often people blame Mr. Nobel for developing explosives which could be used in war, and that's not fair. In fact, Nobel's dynamite is very hard to use in war. What makes war possible is TNT, and that was an accidental discovery. 1897, a carelessly broken thermometer led this guy named Eugen Sapper to identify mercury as a catalyst for the commercial synthesis of the previously expensive dye indigo, the substitute for the purple dye that was no longer was produced from fermented snails. Then in 1928, again, a glass-lined vessel leaked iron into it was defective, leaked iron, which was unexpected contaminant, into some mix of chemicals, and that led Mr. Danvich to chance upon this is a fairly recent discovery, the metallo-organic dye monostrel blue, also a dye which is used quite commonly. Nobel Prizes. Well, here's just a list of some Nobel Prizes. There are more. This is as many as fit on the on a slide conveniently. Look how many prizes are, at least in part, accidental. Nuclear fission, of course, is a particularly remarkable example because it was Fermi who first set out to study what happens when neutrons strike chemical elements, and he found that after the process of absorption of a neutron, an element would frequently turn into the next element up in the periodic table through the process of beta decay. And therefore, when he exposed uranium to neutrons, he thought he had produced elements number 93 and 94, but of course he had done no such thing. What he had been observing was fission, and that was way back in 1934. Had he recognized that his discovery of fission and not been confused by his thought that he had created transuranic elements, the history of the world would have been very different, because the Germans, no doubt, would have developed nuclear bombs before the Americans, and the course of the future of the world would have been very different. So thank God that Fermi was, for once in his life, stupid. Well, all these other, we can give stories about each of these discoveries. Quasi-crystals, tremendously unexpected discovery. CP violation, totally unexpected discovery. The cosmic background radiation, originally thought to be background noise from New York City, later thought to be a consequence of an indirect consequence of birds doing what birds do. But no, it was the cosmic background radiation. Okay, we have no time to go over all of those serendipitous discoveries. Now, when a discovery is made, this has little to do with serendipity, but has to do with the technology. When you have a new idea, sometimes that new idea can be applied very quickly. Now, here we have the example of GMR, which is the giant giant magnetic resistive effect, was discovered more or less by accident, independently by a French and a German scientist. And that led to the possibility of gigabyte hard drives. It took only about 3 years between the discovery and the use of that discovery. From the charge-coupled devices, which were invented, to the digital camera took 6 years. From the transistor to the transistor radio, the Walkman, took 7 years. From the discovery of matter waves, from the notion of matter waves by de Broglie to its observation to the development of the electron microscope took 10 years. From radio waves to wireless telegraphy took only 11 years. From fission to nuclear power took 19 years, from the discovery of fission by Hahn and Meitner and Strassmann to the British implementation of the first nuclear power station took 19 years. From general relativity to the GPS system, which depends on a knowledge of general relativity, took 78 years. And from the photovoltaic effects that were discovered by the father and grandfather of the discoverer of radioactivity back in 1739, anyways, took 115 years. The latency period can have various causes: necessity, such as solar panels; war, such as nuclear power; missing technology, such as satellites and microelectronics, which are necessary for GPS. Okay, next slide. We come back to another industry, this time sugar substitutes. Now, in China, you don't use much synthetic sugar substitutes, at least I didn't see any. Every restaurant I went to has stevia, which is a natural product. But we Westerners like these synthetics. So beginning in 1879, Mr. Konstantin Fauberg forgets to wash up after work. He comes home, notices when he licks his fingers an extremely sweet taste. He had discovered, accidentally, saccharin. A few years later, 1937, Michael Sweda, a graduate student studying a possible anti-fever medication, puffs a cigarette he had left on the lab bench. These chemists were smoking all the time. Most people were smoking all the time back in the old days. And he noticed a very intense sweetness of cyclamate. And here, a bit of a digression. We had two very effective and quite harmless sweeteners, saccharin and cyclamate. The Americans decided that cyclamate causes cancer, so cyclamates were banned in the United States, whereas in Canada, they decided, contrary-wise, that cyclamates were quite safe, but saccharin causes cancer. So there was a period when the sweetener that we call sweet and low would contain cyclamates in Canada and saccharin in the United States because of these conflicting laws. Then in 1965, James Schlatter, searching for a new ulcer or heartburn medication, accidentally spills a promising chemical on his hand, licks his finger to turn the page of his lab notebook, notices that it was something very sweet, discovers aspartame, which is otherwise known as, I forget, but it's a very common sweetener in the United States. We're not done. 1967, accidentally dipping his fingers into the chemicals he was using, Karl Klaus licks them so as to pick up a sheet of paper, thus discovers the magic ingredient of Coke Zero. Coke Zero is of course, a sugar-free form of Coca-Cola, which happens to taste better than most people think, than other, whatever is the secret. Acesulfame is its secret ingredient, not so secret. 1976, in England, a British researcher asks his Indian graduate student to test a chlorinated sugar compound. The student's name was Shashlikant Fadnis. He mistakes the word test for the word taste. So he tastes the damn chemical and thereby chances on sucralose or Splendor, another very popular sweetener. And finally, there's another one which has not become very popular called tagatose, where a certain guy has the hypothesis that an exotic sugar in its left-handed form should be a low-calorie sweetener. He orders the stuff, but is shipped the natural and right-handed ingredient, which nobody had ever bothered to test before, and he found it to be 92% as sweet as ordinary sugar with only 38% of its calories. So it is a natural sweetener, and it's called tagatose. Of course, Americans don't use it. If you go to your medicine cabinet, you will find a variety of medicines, and here are a few of them that were discovered accidentally. Let's just go through. Which ones should we talk about? I don't know all of the histories myself. I don't know how it was discovered that a certain chemical causes hair to grow on the bald head, but it was an accidental discovery. I don't know how it was discovered that a certain drug is particularly effective against the fungus infection of athlete's foot. I do know the story of Viagra, for example, and that's very interesting. That was a large phase 3 test of the efficacy of a certain drug for heart condition. And I think there was something like 150 or so participants in this clinical trial, and half of them had a very strange side effect from the medicine. And that side effect, of course, it was the men who had this side effect, and that was the discovery of Viagra. The clinical trial failed. It had no effect on the heart, no useful effect on the heart, but it had an interesting effect on the penis. Many other discoveries, the mustine, which is mustard gas for lymphoma, that history is kind of exotic because at the end of the Second World War, I think it was the Americans who blew up a British ship or something like that, which was in Italy, and the ship was filled with mustard gas. And the mustard gas spread over the Italian city, causing a lot of injuries, not very many deaths, but a number of injuries. But it was later discovered that the effect of this mustard gas had been, was the first example of an anti-cancer medication, and it led to the development of mustine. And cisplatin, which is a much more commonly used anti-cancer drug, chemotherapy drug, and all the other platinum-related drugs were accidentally discovered as anti-cancer agencies. Of course, nitrogen dioxide was originally used as a recreational drug. It was one of the early 19th century recreational drugs that many famous writers enjoyed using, and only later was it discovered to be an excellent anesthetic for dentistry. So we see again and again how a warfarin, originally a rat poison, is now used as to avoid clots. Let's see, which other one? Thalidomide was a drug which was used in Britain for relieving the anxiety of pregnant women, and it was a disaster. It caused a great deal of injury to the newborns, and it was a terrible, terrible story indeed. But thalidomide was later rehabilitated as a drug for leprosy, but not only leprosy, but for certain varieties of cancer. It is now in use in the medical profession, but not to pregnant women. At home, we have any number of accidentally discovered materials. A Post-it note, we all know, have these little pieces of paper. We write notes on it, and it has a little sticky stuff on it. That was the discovery of a really bad glue, an adhesive, new adhesive that was not very adhesive. And it turned out to have a very useful purpose for Post-it notes, totally accidental. Just look at the list, and why should I even bother to try to explain all of these things? Safety, Corningware was particularly interesting because it's called Corningware because Corning, New York had a glass factory, and it had a great research project, and some researcher had produced a material, a new variety of glass, which he dropped onto the stone floor, and it didn't break. And that was the discovery of cookingware that had been very, very popular for many years. And so you see all of these things, many of them in use today, most of them in use today, vulcanized rubber, etc. Okay. Serendipity in theoretical physics. Yes, there is serendipity in theoretical physics. And sure, I'll just read 4 sentences, 6, 7, however many there are. Surely Maxwell was amazed when he showed that his own equations described the electromagnetic waves we call light. Surely Schrödinger was shocked finding that his waves and Heisenberg's matrices described the very same quantum theory. Surely Dirac was dumbfounded, and he has told me that himself, when he realized that his eponymous equation was, as he told me on the beach in Sicily, even smarter than he was because it predicted the existence of antimatter. It took Dirac several years to figure out that his equation did not. He originally thought it described both the proton and the electron, but he soon realized that could not be, and after a year or two, figured out that there had to be a particle just like the electron with the opposite charge. And like presto, a year after he made this realization, Carl Anderson found positrons. Surely Gell-Mann was gratified when experiments revealed the reality of his quarks, which were originally intended to be purely imaginative constructs upon which to build a more complex theory. Surely string theorists were stupefied when they found their formalism included a theory of quantum gravity. In fact, they've remained stupefied ever since. And surely I was astonished when my early work in 1960 or 1959 culminated in the creation, confirmation, and canonization of the electroweak theory. So there is there is serendipity in theoretical physics as well. I have only one slide left. In the spirit of the superstring, superfluid, superconductor, let me coin super serendipity, which are examples of especially serendipitous discoveries. And those are discoveries in either in pure science or in mathematics, which at first seem abstract, impractical, and of no commercial interest, but which ultimately have the most dramatic and unexpected social and economic consequences. And one is number theory. Number theory was developed, of course, by the early Greeks, but it evolved very rapidly in the 19th century. And G.H. Hardy, one of its exponents in the early 20th century, said of number theory that it is essentially one of the only branches of science that will never have any practical use whatever. And of course, he turned out to be rather wrong about that. Number theory is the basis in many ways, well, to Bitcoin, if you will, but also to secure banking, to so many aspects of the financial world. Who would have thought that general relativity would be necessary to design the GPS system? Who would have thought when I was a child it was still said that there were only 10 people who understood general relativity, and yet it has become something built into a toy that we all carry in our pockets. Who would have thought that Faraday's law would very quickly lead to the electrification of the world? Who would have thought that the World Wide Web, invented by physicists for physicists at CERN, would lead to the internet? Who would have thought that particle accelerators, such as cyclotrons, which were built solely for purposes of pure science, would have evolved into the multi-billion-dollar industry they are today? There are now about 20,000 particle accelerators in existence throughout the world. Most of them are used for industrial or medical purposes exclusively. Among them, for example, are the synchrotron light sources that are of such great importance for industry today. And quantum mechanics. Quantum mechanics, I dream of the wonderful days in the early part of the 20th century when a bunch of kids, most of them under 30, I'm talking about people like Heisenberg and Pauli and Niels Bohr when he made his great discovery, and Marie Curie, she was 30, she was an old lady of 30 when she found uranium. But a whole bunch of people, Jordan was 26, were having a tremendous amount of fun developing a theory of the atom, an understanding of the structure of the atom. There were no IPOs, and there were no non-disclosure agreements, and there was no marketable product. There was nothing. And no lawyers were involved either. But today, 1/3 of the global GNP has to do with quantum mechanics, depends on a knowledge of quantum mechanics. So that's the end of my talk. Serendipity does often play a very important role in science. Thank you all for your attention.
Is there any way to make funding agencies to understand that?
What?
The funding agencies, and you tell them that you do not have to really plan.
How do we convince the funding agencies that they should approve things without an explicit plan about what we will discover when we do not know what we will discover? It's very hard to convince them. Very hard indeed. That's especially true in the medical sciences where the NIH is very reluctant to sponsor research that is not specifically directed toward a specific medical issue.
Other questions?
National Institute of Medicine, NIH. What about my own discoveries? Well, everything I've done is accidental throughout my life. So I remember that some of the work I did which didn't amount to very much actually, but it was a lot of fun, was done with John Iliopoulos on the beaches of Mexico. And we just lie on the beach or go swimming in scuba gear and occasionally converse about what wonderful things we might imagine. There was a lot of accidental, how can I describe it? Let me turn away from the issue of serendipity to the issue of what it was like to be a young and seemingly promising scientist back when I was very young, when I was in my 20s. And the point then there were just problems all over the place that there were not as many theoretical physicists then as there were today. So there were more problems and fewer people looking for solutions. So that I remember when I first showed up at Copenhagen in 1958, I got my degree in 1959, but I had completed everything in 1958 and went to Copenhagen. Okay, what's serendipitous? Why did I go to Copenhagen? I had planned to go to the Soviet Union for stupid reasons, perhaps having to do with the fact that my parents were born in Russia. They never wanted to think of Russia again after they came to America, but nonetheless, there was a cultural interest. I wanted to spend a year as a postdoc in the Soviet Union. It was a stupid idea, I know, but whatever. And arrangements had been made, and I was going to go to I wanted to work with Tom at his institute, but instead I was supposed to go to the Steklov Institute, and all arrangements were being made for me to go to Russia, except that I didn't have a visa. So without the visa, I couldn't do that. So I wrote to Niels Bohr, and I said, could I come to Copenhagen for a few months until I get my Soviet visa? And he said, sure, come. So I went to the Copenhagen Institute, and there I met some Russian and Chinese postdocs, as well as from the rest of the world. And my Russian postdocs introduced me to their friend, the Soviet consul in Copenhagen. So we invited him to our parties, and each time he came to the party, he'd give us some vodka, which was a very nice gift. And each time he came, I would say to him, is my visa coming? And he would say, visa coming. So good, visa coming. After 3 or 4 months of visa coming, I decided I would be more careful about this and go to the Swiss consulate and ask the Russian consul in Switzerland about my visa. So I went down to CERN, where I was spending part of my time at CERN, and went to the consulate in Bern and asked the Soviet consul, is my visa coming? And he said, visa not coming. And so that was the end of my Soviet dream, and I always thank my stars that I was lucky enough not to get a Soviet visa, because it was in Copenhagen that I wrote the paper that earned for me the Nobel Prize. That was serendipity.
I'm sorry, I had the same question, but I still want to thank you about it. I still have the mic, so I still want to thank you for the very inspirational talk. Thank you.
Thank you.
Okay.
Sir, thank you for the talk. My question is, sir, how would you describe a serendip event in terms of mathematics? I mean, like on an introductory basis. I mean, nothing is finalized, so.
Well, I'm not quite sure of the question.
Sir, how would you describe a serendip event in terms of mathematics?
How would I describe?
Well, do you know of an example in mathematics? Serendipitous
Of
discovery.
serendipity in mathematics. But offhand, I don't recall an example of serendipity in mathematics.
Sorry.
Do you?
Sir, my question is, how would you mathematically describe a serendip event?
I'm sorry, yeah, so misunderstanding. So he wants to know, is there a mathematical description of serendipity?
Is there a mathematical description of serendipity? I don't know. Is there a mathematical description of love? Or of a nincompoop? No, I don't think there's a. The point is that often when we were looking for one thing, we find something quite different. And take, for example, our most serendipitous of all friends, the discoverer of radioactivity, Henri Becquerel. He had this theory that he was favored, that he believed in, and his experiment, he suddenly realized that his experiment was a complete failure. That is to say, it proved that his idea was absolutely wrong. But he realized that he had discovered something else which seemed to be even more interesting and even more important, that this material, uranium, in any chemical form, would continue to emit radiation, very intense, very energetic radiation, indefinitely. And the problem immediately arose in his mind and in the minds of many people like Niels Bohr and Madame Curie, that perhaps the law of energy conservation was wrong, that there appeared to be an eternal source of energy in things like radioactivity. So that was he was brilliant, not because he had that idea, but he realized the importance of his discovery of what he called uranic rays. He realized it was something new, something important, and something far beyond the idea that he had at the beginning. He was willing to abandon his previous line of thought completely and focus on the new discovery, in which he made serious contributions after his original discovery. So it's not enough just to see something unexpected, it's to exploit that new observation, to make use of that new observation, to forget about the garbage you were doing before and focus on the new thing, the new boy on the block, the new drug, the drug that had strange consequences on men, the drug that exploded, the yellow dye that tended to explode. You have to recognize that what you were doing in the past was nonsense and was irrelevant, and you had discovered something much more important.
I have a philosophical question, okay? Now, since you give us so many useful examples about the usefulness of serendipity in scientific discovery, how would you advise the leadership of like a university or the leadership of society how to encourage the use of serendipity for future scientific advancement? For example, should we encourage more wide idea, encourage an atmosphere of trial, or more, I would say, tolerant on failure of the scientists? So how would you advise that these leadership people and make serendipity more useful in the future?
Well, certainly, this past week, I've spent some time consulting with various industries in China, in mainland China, about their research endeavors. Some of it quite exciting indeed, but I did find that there was a lack of open-mindedness, that the research endeavors that I found, the researchers that I spoke to, were highly focused on what they were doing and dedicated specifically to the goals of the company, the immediate goals of the company. And there did not seem to be any leeway, to be any open space for them to think about what they were doing and think if perhaps there was another way to do it or a better way to do it or a way, perhaps an indication of something they had not expected. I didn't see that kind of spark there. I don't know what things are like in industry. Here, I know that it used to be true in large industrial companies in the United States, like AT&T or General Electric, that a great deal of, and many other companies as well, that they maintained large groups of research scientists and gave them a lot of independence in their research activities. And as a consequence, at AT&T, for example, I think there were 12 Nobel laureates that were associated in one way or another with AT&T when their discoveries were made. And that's quite remarkable. And that attitude no longer, that AT&T laboratory no longer exists as such because of the various regulations that have gone into effect. And it's much more, now you have companies like Google, perhaps, who are replacing the industrial labs of the past, but is Google ever going to come up with a Nobel Prize winning discovery? I don't know. But yes, there was a time when industry played a very interesting and important role. And today, that with the focus on the immediate dollar and the stock market behavior within the next quarter, the short range that is permitted for research, it is much more difficult to imagine industry providing the kinds of new devices and new ideas that we need. Those ideas must come from universities where people are free, as they are here, to pursue research in whatever direction that they feel is most promising. And that is the larger role that in the future must be played wholly by academia. That's why places like this are very, very important for the future of science.
So, were you surprised by the,
By the what?
By the Japeside discovery, given that it was
The
predicted by
Japeside
your...
discovery, was I surprised? Indeed I was. That's a fun story because I was at home sleeping on that Thursday, I think it was, and Samuel Ting, we know, who was my good friend for many years, still is my good friend. In fact, we just were in Stockholm together for the Nobel ceremonies. Sam Ting called me up on that day in November of 1974, and he said, "Shelley, come to my office as soon as you can." So I got dressed and drove to MIT and went to his office, and he showed me the discovery of the J particle. And indeed, it's called J because Ting looks like the letter J. In fact, the other day I was at a meeting, industrial meeting, and there was a woman with a name tag with that, and I said, "Madame Ting," and she looked at me in surprise because clearly I didn't know one word of Chinese, but I saw her name tag and I called her by her name. That impressed her very much. Yes. So anyway, Ting called me and showed me the data, and the data was spectacular. There was no question that he had discovered a new particle. It was not obvious to me at the time what the hell it was. That's certainly true. But I went into my car and drove a short distance to Harvard, to my office at Harvard. And then I ran up the stairs and I said, "I have something exciting to tell you," to whoever was around at the time, Howard Georgi and Alfred de Rucola, whoever. And they said, no, we have something to tell you. And they told me about the discovery by Richter of the psi particle, which was called psi not because of Richter's name, but because the event, the most convincing event, looked like the letter psi. So we were briefly confused by that, and it didn't take very long before Alvaro de Ruchala and I wrote a quick paper saying, has bound charm been discovered? And that was an interesting time, because in the first issues of the Physical Review letter of the next year, there were many different explanations were offered for what this particle was. My thesis advisor, my beloved thesis advisor, Julian Schwinger, who was the person who told me to spend my life on the Electro Week idea, he was convinced that the particle was his latest theoretical creation, the dion, which was a false theory that he had recently, at that time, invented. So he said it was the dion. My dear colleague, Mayani, with whom I had done the work on the Iliopolis-Mayani, the Jim mechanism, he had written a paper saying that the new particle was the Z boson. And so it went. There was crazy article after crazy article. I think there were only two that got it right, one from the Princeton group and one from the Harvard group. So that was a very exciting event. Was it a surprise? Yes, it was a surprise. Shouldn't have been a surprise. Should have realized that there would have been such a particle if there were such a quark as that I had imagined. But I was too stupid to predict it. I think the only person who predicted it is a guy sitting over here. You anticipated the discovery of the J psi, as I recall. Yeah, didn't you? I thought you had some. Nobody anticipated it. If it wasn't you, it was nobody.
Hello. How do you keep an open mind about your job, about your research, with avoiding the stress of getting the results? I mean, you may be too focused in something to recognize an event of serendipity next to you. You may be too obsessed with the results. So is there a recipe to be open to follow other research?
Is there a recipe for serendipity?
Being open.
To be able to recognize serendipity, I mean.
I have no way of anticipating serendipitous discoveries or suggesting ways in which you can best do that. I can only describe what has happened in the past. I know nothing of the future. I would hope there'd be some totally unanticipated discovery, even still from the Large Hadron Collider. It is possible that they can find evidence among the accumulated data for something that they had not looked for that is there, and that is there even with convincing evidence. Because it's not clear to me that they have explored every channel of what could possibly have happened among events at the Large Hadron Collider. So perhaps with an open mind, experimenters can go over old data and find new discoveries. Some people have claimed to have done just that, but I don't give them much credit for that. I'm not convinced that they have done so. But it's always a possibility. There's something we're missing. There's Peter Voigt, who's another critic of string theory, has written a very fine book in which he argues that there has to be something else. There has to be someone somewhere has to find that something else that we are missing. There's a clue that is just missing our thoughts. I'm sure there is something like that, and I'm sure that someday someone will be lucky enough to spot it, but I don't know what it is.
So what would you suggest your student to do? I mean,
I no longer suggest anything to students. I am about to retire from active duty at my university, and I will now spend time writing for various books and doing some consulting work and working on it, hoping to have some interesting theoretical idea, but I'm not depending on it.
So Shelley, again, has inspired me to sit back and think about the serendipity, because for all of us, we are always thinking about how can we advance science, how can we make this kind of go on. And it's clear to me that over my lifetime, I've seen different people follow different strategies. You have a strategy that I think I have. Other people have different strategies. For me, I would, depending on serendipity, that I would do many experiments where I was looking to find some unexpected thing or something else. But it was very important for whoever you are to have a really strong background and look really carefully at your results. It's very seldom that you do an experiment where you walk around the corner and you see the moon, and nobody had ever seen the moon before, right? It's seldom that you see something so overwhelming. You're only people who get to do stuff like that are people who get to build a great new facility, like they build the first giant electron microscope or the great accelerator, and they get to be the first one to see this new data, and then the serendipity discovery is relatively straightforward. Most of the time, you have to have a very strong background, and you have to be very strong about looking at the answers and saying, do these make sense? And I had some idea in mind, but now I see something. What does it mean? What does it mean? And I looked down that list of stuff you have, and most of those discoveries are people who looked very carefully and very rigorously and teased out the result and so forth. And that's the strategy that I try and follow by doing experiments. For you, your strategy that I saw often as an inspiration anytime is you had a lot of great ideas, and some of them were really worthwhile. I mean, some of them were really outstanding.
And some of them are junk.
Right. And some were wrong, right? But at least they were wrong. We know some people have ideas that aren't even wrong, right? But the fact is, it takes a certain level of background and knowledge and deep thinking to throw out ideas, to be brave enough to throw out an idea, even though you know some are going to be wrong. And so that was the inspiration that you've been to me, which is that you had a lot of ideas and you put them out there. And yes, some of them were wrong, but some of them were great, right? And you should blame yourself about charm. He had the idea about charm. He should have predicted the Chase-I. But I mean, I have mistakes like that too, where I should have predicted the dark matter work, the dark energy, because I knew the answer was off by a factor of 2, and I just didn't understand to push it as far as it had. But the fact is, you get serendipity not by, it takes an incredible situation to put yourself in a situation where you built a new tool that lets you see the universe that nobody's seen before. That's very rare. It's more that you've made an incremental change and you see some small effects and you've got to tease it out, and you have to have that kind of training. And so there is a way to do serendipity, right? The best way is to have a huge amount of money and get to build a great new instrument. The next best way is to have some amount of money and build new instruments and do new, or to have very rigorous training and have great ideas. And so you've been a Mr. Ideas guy.
Yeah, and one of the ideas that I was most proud of is an idea I shared with Howard Georgi, was the idea of a unified theory of strong, weak, and electromagnetic interactions. And we were working on that idea and then came up with the paper we eventually would write. And we were terribly surprised, and at the same time, I mean, it's a paper which, when read by the outsider, it sounds like it has to be true, it has to be true, it has to be true, except then we conclude that the proton has to be unstable and has to decay. And it even wasn't possible in those days to make an estimate of what the lifetime of the proton should be. And with Weinberg and others, a prediction was made that it had to be around 10 to the 29th years. So we had a beautiful theory, a theory that had to be true. It was too beautiful not to be true. But the truth of the matter is it's not true, and it didn't work. That was, in a sense, my biggest disappointment, probably Howard's also, that SU5 didn't work.
Well, it still might work, right?
Well,
I mean, the original version that you proposed did not work, but...
well, it worked, but until people bothered to work out the consequences in detail, right. You had to show that it didn't. When it first came out, no one was prepared to say it didn't. People were not thinking about the coincidence of coupling constants as carefully as they became afterward. That things changed. But the idea on the face of it, before it got quantitatively rejected, clearly had to be true. Till it was realized that the proton did not have the predicted lifetimes, the coupling constant did not come together, etc.
You know, what I had in mind was the fact that I'm sure you know, even if you don't particularly fancy the idea, which is if you make your SU5 theory supersymmetric, then you can solve the meeting problem.
Yes.
And potentially also the stability problem.
Oh, there were lots of people jumped in the game and tried to save the theory in one way or another, but at the moment, my faith in supersymmetry is much less than the... I know it's a European religion, but it isn't an American religion.
Okay, I think on that note, we should thank Shelley again, and we can retire outside for some refreshments.
Thank you very much.